Hi, this is the first mini lecture which concerned with analysis of sequential systems containing not only a single element but at least two. As you can see, NAND gate is connected with the feedback connections with a T-type flip-flop, and let's decide it will be a positive edge triggered one. And analysis will include, first of all, deriving state transition table. Then from this table we will get state transition equations. Then we construct state transition diagram. And for example timing, we'll finish the analysis. Let's start with the first. A state transition table will contain two so-called input columns, which is X, which is input of the system, and state of the system. State, as you remember, is the state of the memory elements. It's a value of Q always, not this one inverted, but this which is not inverted. And that's all. So we've got four cases in this state. Always. This is all inputs apart from CK. CK is never present in this table. And all state bits. So simply these are Q outputs of the all flip-flops in the system. In this case we've got a single one, so only one state bit is present in the table. And what's on the right hand side is the next state of the system, which is the next state of Q, the same Q, and output, the state which is present on the output. You can expand this table if you need to put the input of the flip-flops. Here we've got only one input, T time. CK is not present in this table, never. And before you begin filling in the next states, it is wiser or simpler to find T first, and then decide what the next state will be. So T is simply NAND of Q, and this is NAND of these two columns. 0, 0 NAND is 1, 0, 1 NAND is 1, 1, 0 NAND is 1, and 1, 1 NAND is 0. Okay, now we know what the next state will be. If you have a T equal to 1, the next state will be inverted. The same is true here, inverted. The same is here, inverted. And in this case, it will stay the same. 1, 1. No inversion, no change. Okay. And what about Y? Y is simply not Q of T, but is taken from the T time T, not T plus 1. So before change, not after. This is the common mistake students do. Okay, taking this value inverted instead of this. Okay, so you must be aware that it is a 1, 0, 1, 0. This is the inversion of Q of T, not Q of T plus 1. Alright, so we've got the first. The second is to derive the state transition equations. STEs contain only, please don't put too many equations here, only Y of T equals and Q of T plus 1. All the outputs and all the state bits must be included in the STs and no more. So Y of T, as you can see here or here, is simply Q of T inverted. Q of T plus 1 is this function. It is a function of these two variables. And as you can see, there is a single max term. The max term is the sum. So it is that sum of X and Q of T. And which one must be inverted? Q of T. So it is X plus not Q of T. That's all. no more elements in the STE. Don't put the equation for t. It will be a mistake, okay, in the test. Next is the STD. So this is the third point, is the STD. It comes from rather table, not equation. It is easier for me to do it this way, but if you have if you adopt another way, it is also allowed. The result is important, the final result. So first we must analyze it and find if it's Moore machine or mini machine. Y is is dependent only on Q on the memory. It is not dependent directly on X. That's why it is a Moore machine. Machine. So it is important because the conventions of drawing the diagram is different for Moore and for mini. What's inside the circles in Moore machine? On the left hand side you've got the state bit, which is this Q, which is first. Then is the slash and Y follows. Y is inverted Q. That's why I put 1. And the opposite. If Q is 1, Y is 0, which is here, and also here, and also here, Y is inverted Q. Okay, we've got two states with the output shown within the circles. And now we draw, each row has its interpretation, its counterparts on the diagram. The first row tells you that you go from 0 to 1, from 0, Q, to 1. This arrow, and when there is X equal to 0. That's it. Next row gives you the opposite change from 1 to 0, for X 0. Next row 0, 1, already drawn. Arrow from 0 draw is, so don't draw another one, but simply put comma and put the new value, another value for X, for which the change occurs. And the last row tells you no change. If you are in state 1 is this, no change for X equal to 1. And now the diagram is complete, and that's all. As the last point is to draw the timing, the example timing. You will be given X, let's say this, and CK, let's suppose it's this CK signal, and your task is to draw Y. You can also, if you want, first draw Q and then Y. It is especially important drawing Q in the case of mini machines, Moore machines, because Q will depend, Y will depend not only on Q but also X. So Q must be combined with X using a function of Y will be easier to do it in this form. First draw Q and then draw Y. And let's do it in this case as well. So let's try. What we must know, the tree-gain condition. Let's assume it is rising edge. So we must stop at each rising edge and decide what to put on the output. And what else? We must also have, for the analysis, that Q of t equal to 0. So at the beginning of the analysis, the Q was 0. Let's say, or 1. It depends. It will be given to you. So, because we are here at the beginning, y is equal to 1. So we must start with 1. And q with 0. On the rising edge, we've got x 0, so we must follow this arrow. So q will change to 1. And we must stop here. We must stay in this state until the next. And the same is true for this. Let's look. We are in state 1. Q is equal 1. And there is 1 on x. That's why we stay in the same after clock, in the same state. And the same follows here. So until the end. So because y is the inversion of q, you simply mirror. You can mirror it, invert it, and you've got it. It was quite easy to obtain. In the case of Moore machine, it is easier than in the case of Mealy machines in general. And Mealy machine will be presented in the following analysis example. Thank you.